we all know that the set of prime numbers is infinite. All of us know this fact and we take it for granted. The proof was given by Euclid in around 500 BC, as early as 500 BC, and this proof was published in his work, The Elements. And the proof is really very, very simple. So I will try to explain the proof here in this video, but before going into the proof, I want to also mention a short story. The story goes like this. Now, since the proof is very simple, I usually ask my students who come to class 9 from 8 fresh to try and give a proof of their own. Now, a few years back, I asked the students of class 9 to try, and as usual, within a few days, most of them forgot about the request. But one student was very, very sincere about mathematics. She tried the proof for the entire year, and when she was promoted from class 9 to class 10, even 3 to 4 months into class 10, after that she came up with a proof, and I was so surprised to see that the proof that she has done is completely different from Euclid's proof. And it was a very, very elegant proof, and I was really pleasantly surprised. So she had that original thinking inside her. So what I'll do is, I'll divide the total video on this proof into 2 episodes or 2 parts. Here in the first part, I will explain Euclid's proof, and in the second part, I will explain my student's proof. And you will see how beautiful the proof is, the one she has come up originally. Okay, so let's start. So what Euclid exactly proved is, the statement was that the exact statement was, given any finite set of prime numbers we can always find a prime number not in the set, not in the given set. So you understand the essence of the statement. You give me any finite set, I will find a prime number which is not in the set. So that essentially shows that the set of prime numbers is infinite. Now note one thing, that the new prime number that we will find, it is guaranteed that it will not be in that set, but it can be less than or greater than the primes present in the given set. So at the end, I will give you 2 examples where you will see both the cases occurring. Okay, so let's start the proof. Let A equal to P1, P2, P3, Pn be any finite set of prime numbers such that, since they can all be ordered, so without the loss of generality, we assume that they are in this order. So that means this set is just any finite set of prime numbers. That is, we assume that the set of the set of prime numbers is finite. So you can say this is actually, we are taking the help of method of contradiction. Method of contradiction. This is the method we will apply here. Okay. So Now, you all know that the prime numbers start from 2 and then 3, 5, 7, so on. So, this set could start from 2, 3, 5 like this, or suppose we don't know that this prime number start from 2. In that case, this can be any set of primes. The assumption is just the set is finite. That is, we know only a finite set of prime numbers, and since there is an order between them, we arrange them like this. This is the order we arrange them. Now, see what we do. Now, we construct a new number, a totally new number, and let that number be capital N. And how do we construct that new number? These finite number of primes, we take the product of them. So, P1, P2, P3, dot dot Pn. And then add 1 to it. So, we have constructed a new number, a completely new number. Now, this new number, there are only two options for this new number. Either it is itself prime or it is not. So there are two possibilities. First possibility is n is itself prime. So in that case, we get a prime number p not belonging, we get a prime number p, we get a prime number n which is not in the set A. Sorry guys, I made a mistake here in this part. While I writing this, I said we got a new prime number n not belonging to A, and I use this symbol. So this is wrong. It will be we got a new prime number n not belonging to A. So I just wanted to rectify my mistake. Okay. So the rest is okay. So we have found a new prime number. But it may so happen that the number n, the new number n that we have found, is not prime at all. So it is composite. That might also happen. So let's see what happens in that case. So the second possibility is n is not prime. That is, n is composite. Okay. Now, if n is composite, then we go one step further and we say that if n is composite, in that case, there will exist a prime number p that will divide n, that will be a factor of n, and this p will not be equal to any of the p1, p2, pn's present in the construction of n. Okay, so this fact, if n is composite, this fact guarantees that there exists a prime number p which is not equal to p1, p2 or pn, such that p divides n. Now, why is this happening? Why? How do I know? First of all, since it is a composite number, you know definition of prime number is it is divisible by 1 and the number itself. So, since it is a composite number, so there will be at least another factor different from 1 and the number itself, that is n. That means if you do the prime factorization of n, we'll end up with at least one prime factor, and suppose that is p. And I also claim that this p will not be equal to any of the p1, p2, pn's present in the construction of n. Why? Let's see. If p is equal to any one of these numbers, suppose p becomes equal to one of them, say p2. then what will happen? In that case, okay, so what happens is, then you can see in we can write this relation that we have written here. This can be written as n minus p1, p2, p3 dot dot pn equal to 1. So if suppose the prime factor of n is p is equal to p2, so what do we get? P2 divides both n and this portion. So what happens is this will imply that p equal to p2 divides both n and p1, p2, pn. So that will in turn imply that p divides 1. And that is really absurd, right? So we can safely assume that this new prime factor of n will not be equal to any of the existing primes p1, p2, pn. So that's it. Now finally what we got is a new prime number p which is not in the set. But initially we said that this A set containing P1, P2, P3, Pn is the finite set of primes. So naturally that contradicts the fact that A is finite. So we get, therefore, we get a new prime number P not belonging to the set A. But this contradicts the fact that A is the set of we can say is a set of is a finite set of all prime numbers. So ultimately what we saw is, you give me a finite number of prime numbers, any finite set of prime numbers, I will be able to construct a prime number which will not belong to that set. So naturally our assumption that the set A was finite is not true. So final conclusion is, therefore, let us not use A. Therefore, the set of prime numbers is infinite. Now, let us take two examples. First example, let us take A set to be, let us start with, since we know 2 is the first prime number, so let us suppose it is, the set contains the prime numbers 2, 3, 5. Let us keep the examples small for better understanding. So as if this is the finite set of prime numbers that exist, 2, 3, 5. Now, according to the definition of n, it is the product of 2, 3, 5 and 1. So that becomes 30 plus 1, 31. So this is the new n. This is the new n, and here in this example we see n equal to 31 is a prime not belonging to the set A. So that is what exactly what was claimed earlier, and we see that happening in this example. Now let us take another, and so you see you got a number 31 which is greater than the greatest number here, the 5, that is 31 is greater than 2, 3, 5, all the prime numbers, it is greater. But is it so that the new prime number that we will get will always be greater than all of these? Let's see. Let us take another example. Say a equal to 5, 7, 11 and say 13. So now I start the finite set of prime numbers not from 2, from 5, because in the proof it said given any finite set of prime numbers I should be able to find a new number. So what's the new number here? So new number is 5 into 7 into 11 into 13 plus 1, and that is equal to, if you calculate, it will come out to be 5006. And 5006 you can see is not prime. So as I said in the proof, the new number formed will either be prime or it will be composite. So in the first example we saw n itself was becoming prime. Now this is composite, not prime. So in that case we mentioned that I will be able to find the prime factor of this composite number which is not present in the set A. Now you can see this, if you prime factorize this, one of the prime factors is 2. So here what do we see? Now 2 is a prime factor of 5006. So ultimately what we saw, we found another prime number, prime number 2, that was the P in our proof, which is not in the original set A. And also note that here the new prime that we have found, that is not bigger or greater than the existing set of primes. So it might be, it might not be. That is not the issue here at all. The issue is I should be able to find a new prime that is not present in the given original finite set of primes. So the proof is really very simple to understand, and all of you must keep it in your mind. It's a beautiful proof. Now, so this will be the part 1 of this video. I will make a part 2. So make sure that you see that video also to see how beautiful the proof given by my student is, and that was completely original. Okay, so I think, I hope rather, this video was useful to you. You could understand the proof easily. If you think it's so, then please you put a like and also subscribe to my channel if you have not already done so. Thank you very much.